In section 4.4, we're going to be doing modeling and optimization. We're going to be talking about how do we find the maximized or minimized amount of certain things. Mainly this happens with products. So when we're talking about minimizing cost, or when we're talking about minimizing the amount of material it will take while maximizing a volume, how much it can hold. Think like soup cans, pop cans, that kind of stuff. So here is the process that we're going to be using to solve any of these max-min problems. I'm going to let you just read through that at some point. But the biggest one that we have to remember to do is go back and interpret that solution at the end. Does our answer make sense in the context of our problem? We're going to be doing lots of calculus to figure these out. There are algebra ways to do most of these as well. But make sure when you're doing it on a calculus test that you're showing how the calculus applies. So we did an activity last week where we talked about how to find the biggest box. So just to reiterate that particular example. In example 1, it says we have an open top box. We don't have a top on it. And we're cutting congruent squares of side length X from the corners of a 20 by 25 inch sheet of tin and bending up the sides. How large should the corners be to make that box hold as much as possible? And we're going to figure out what it's that maximum volume. So first off, let's draw a picture of this situation. So I've got a 20 by 25 sheet of tin. So we're going to say this is the 25, this is the 20. And we're cutting corners out that have a dimension of X by X. So that when we cut it out, we can fold it up. So now my new length of this box is 25, and I'm taking away X and X. So 25 minus 2X. And then the same thing happens here. This was 20, and I'm taking away X and X. So 20 minus 2X. So to find the volume of a box, we do the length times width times the height. So in this case, the height of the box, when I fold this up, is going to be just plain X. So we have X times 20 minus 2X times 25 minus 2X. Now I want you to think here about what the domain and the range of this function might be. So when we're talking about the domain, we're talking about the X values. And if this thing is only 20 inches wide, if I cut out an X value of halfway, then I'm essentially removing the width completely. So I can't ever have an X value bigger than 10. And I certainly can't have an X value smaller than 0. So we're looking at a domain of 0 to 10. And then our range, when we're talking about how much this one can hold, the most it could ever hold would be if I cut out 0 and 0, so 20 times 25. So we're going to go 0 to 1,000. Now, if I asked you back in Algebra 2, how would you find the maximum of this volume? In Algebra 2, I would hope you would just graph this and find the maximum. So what I want you to do is do exactly that. We'll do the calculus to verify this in a moment, but punch this into Y1, and I want you to put this window in, find the maximum value. All right, so I graphed the function, I found the maximum. We get 3.681, 820.528. So we need to realize what these values actually mean. This is our X value, this is our volume. So this is the length of one side of a square, and this is the resulting volume. So that answers that second question. The resulting volume was 820.528 cubic inches. But then the other question that this asked was, how large should the squares be in order to make this possible? So a square is a length times a width. I want to know how big is the square. And so we know our X value was 3.681. So 3.681 squared. And if we do that on our calculators, 3.681 squared we end up with 13.5497, so 13.55 inches squared. All right, so to use calculus to do this, it would take a lot more time, so I'm going to just leave this one. But when we're trying to maximize a function, the way we maximize is you find the derivative and set it equal to 0. You're looking for those critical points. So this one you would just have to distribute this all the way out, find the derivative, set it equal to 0, and you would get the exact same x value. So I want you to realize there's multiple ways to solve these different types of problems. So when we get to example 2, this time it says we have to design a 1-liter oil can shaped like a right circular cylinder, and they want to know what dimensions we will have to use to get the least amount of material. So when we're looking at this one, we have to use surface area and volume of a cylinder. Now, first thing that I want you to know is a 1-liter oil can is the same thing, 1 liter, it's the same thing as 1,000 cubic centimeters. So when we're talking about volume, those are equivalent. So when we're talking about volume and surface area of a cylinder, these are those formulas from geometry we said, don't forget how to do all of these, and we forget. So volume of a cylinder is pi r squared h. Surface area of a cylinder is 2 pi r h plus pi r squared. Sorry, it's 2 pi r squared. There's 2 circles. So if you think about a cylinder, you've got circle, circle, and then if you were to cut this apart, you've got this rectangle. The length of the rectangle is the circumference, which is the 2 pi r, and the height of the cylinder is h. So there's my cylinder, here's my 2 formulas. Here's what we know. We know that the volume of this cylinder is 1,000 cubic centimeters. We're trying to minimize, find the least amount of surface area. So in order to do that, we have to do a derivative, or we could graph it, but the problem is we have 2 variables. So I need to use this function to help us get rid of one of these variables. And so I look, there's only one h in this question, and I can solve this equation for h. So h equals 1,000 over pi r squared. And I'm now going to use that to plug into this equation. So go ahead and plug in the h and get a simplified equation. All right, so we get 2 pi r h, the pi's cancel out, one of the r's cancels out, 2 times 1,000 is 2,000. So now I want you can either find the derivative and set it equal to 0, or you can graph this and find the minimum. You choose, but I want you to come up with what are the dimensions. I want you to first find r. All right, I did the derivative, and I rewrote 2,000 over r to be 2,000 r to the negative 1. So I got negative 2,000 r to the negative 2 plus 4 pi r equals 0. I wanted to get rid of this r squared on the bottom, so I multiplied the whole thing by r squared. So I get negative 2,000 plus 4 pi r cubed equals 0. Add the 2,000 and divide by 4 pi, and then cube root. So I end up with 5.419. So that's the radius of this can. The question is, what dimensions will use the least material? So I'm still missing one dimension. I still have to figure out what h equals. So we do have this nice equation up here for what h represents. So take a minute and plug in 5.419 in for r to figure out what h equals. When we plug that value in, you end up getting 10.8395, so 10.840 centimeters. So these are the dimensions for the can that will hold 1 liter of oil and use up the least amount of material.